In Excel, the IMARGUMENT function takes in a complex number and will return the argument of that complex number, which we generally represent as theta, where theta represents the angle that we need to take to end up at the complex number when we plot the complex number in the complex plane. Now, the function is quite straightforward to use, so we write =IMARGUMENT, and this will return the argument q, which is an angle expressed in radians. And so we supply to this the complex number. Now do keep in mind, complex numbers in Excel are considered to be text or strings, so we can't make normal calculations with them. In this case, the imaginary part is denoted with an I. This could also be a j. I close the parentheses and I pull this down, and there we have the angle theta. Now, this angle theta can also be calculated by taking the arctangent of the imaginary coefficient divided by the real coefficient of the complex number. So let's try this. For this, we can use the atan2 function, which will return the arctangent of a specified x and y coordinate in radians. Now, we need to supply an x number and a y number. Now, if we look at the complex plane, the x-axis will contain the real numbers, whereas the y-axis contains the imaginary numbers. Now, there exist functions within Excel that allow us to extract the real and imaginary coefficients from a complex number. So for the first argument of the atan2 function, we need the real coefficient of our complex number, and we can get this through the imReal function. I supply to this the complex number, and so this will return the real coefficient, in this case being 2. Now then we need the y number. The y number is the imaginary coefficient. So for this we can use the imaginary function, which we supply with a complex number, and it will return the imaginary coefficient of our complex number, which in our case is also 2 again. Now I close these parentheses and press enter, and let me pull this through. Now, as you can see, we are getting exactly the same result as if we took the IMARGUMENT function. Now, of course, it was a little bit more convoluted, but you can see where it's coming from. Now, what is actually the point of calculating this argument of a complex number? Well, in column A, we have the complex number, and it is specified as a rectangle form, where we have the x-axis, and that is a real part of the imaginary number, and then we have the y-axis containing the imaginary part. And so then we can plot each complex point as a coordinate defined by the real and imaginary coefficients. Now, that's one way to define a point on a plane, but you could also define the point through the distance from the center at a certain angle. And this argument, this theta, is exactly what this angle means. When we use this form, where the distance is r and the angle is theta, we call this the exponential form of the complex number. Now let's recreate our complex number using this exponential form to prove that we will end up with exactly the same complex number. Now the first thing we need to do is to multiply theta, our argument, with I. Now we can do this using a function IMPRODUCT. We cannot simply do this with a regular asterisk or regular multiplication, because we cannot multiply with complex numbers, as they are considered to be strings or text within Excel. So the first argument will be a y in double quotation marks, because remember, it's text. And then the second argument, which you want to multiply, that would be the theta. So this was calculated here with the IMARGUMENT function. I could have also used the result from the arctangent function. Now I close the parentheses here, and now the number that we are getting here, we need to take the exponential function of that. So for this we can use the imexp function, which will return the exponential of a complex number. So this will give us e to the power I theta. Now once again, we need to use a special function here, imexp, that works with complex numbers. Okay, all that's left to do is now multiply this result with r, which is defined as the distance from the center of our complex plane up until the complex number. So for this, we need to use, once again, the IMPRODUCT function in Excel. And so we multiply r times the number that was returned from the exponential function. So let me close the parentheses here at the end, and now we still have to define r. Now r, like I mentioned, is a distance from the point to the center. Now within Excel, there is an easy to use function that we can use to derive this r, which is the MABS function, which will return the absolute value of a complex number, which we also call the modulus, which is equal to this r. So once again, it takes in one argument being the complex number. So I click on that, I close the parentheses and I press enter, and I will be pulling this through. And as you can see, we are mostly getting back the exact same results as you can see. Now, sometimes there's a slight discrepancy, and that has of course everything to do with some rounding errors within Excel, but you can see for the most part, it's actually matching up. So to recap, we can use the IMARGUMENT function. We supply a complex number to it, and out comes the argument of this complex number. This argument is often represented with the Greek letter theta, which represents the angle we take from the x-axis on the complex plane to arrive at our complex number. Thanks for subscribing, and leaving an optional tip, consider watching this video next.